Good day and welcome back to part 4 of our discussion on how derivatives affect the shape of a graph. As indicated at the end of the previous video, you can find an associated class worksheet located on Canvas. Hopefully you've done this and worked through several of the problems. In this video, I'd like to go through problem number 2 and really just focus in on the new material related to what the first derivative and the second derivative tell us about the shape of the graph. So for the function x times the square root of x plus 3, I'm going to leave the details to you, and you can certainly find more work on the typeset solutions located in Canvas, but if you were to differentiate this using the product rule combined together into a single fraction, you could find f prime of x. And then similarly, if you were to differentiate this with, say, the quotient rule and do some simplifications, you can find this formula for f double prime of x. In this video, I want to focus in on how we can use these formulas for f prime and f double prime to determine things like, say, in part A, the intervals of increase and decrease from f prime, and in C, the intervals of concavity from f double prime. So the first thing we're asked about in part A is to determine those intervals of increase, decrease, which correspond to where the first derivative is positive and negative, which of course first requires us to think about where it is equal to 0. So if we set this equal to 0, we can note that a fraction is equal to 0 precisely when the numerator is equal to 0. So that would be 3x plus 6 is equal to 0, or x is equal to minus 2. Now, I do want to be a bit careful here to note that in terms of our original function f, the domain is from minus 3 to infinity. Whereas for f prime, we can only plug in quantities bigger than minus 3 because minus 3 would require us to divide by 0. So note, the domain of the function f is minus 3 to infinity. The domain of the function f prime, however, is the interval from 3 to infinity. And hopefully what you see is that there is a more subtle type of critical point. There's a critical point at x equals minus 2 because f prime is 0, but there's also a second critical point corresponding to minus 3. So I'll just note the critical points are minus 3 and minus 2. In terms of where our function is positive and negative, we need to look at in the domain. So for inputs bigger than or equal to minus 3, and we know that f prime is equal to 0 at minus 2. This requires us to think about the sign of f prime on two intervals, from minus 3 to minus 2, and when you're bigger than minus 2. So we could just check a sample point in each interval. So for example, if we were to substitute in 0, we would have 3 times 0 plus 6 over 2 square roots of 0 plus 3, which is positive. So for any input to the left of minus 2, f prime will be positive, which indicates that our function is increasing. Then we need to do the same thing with a sample point in between minus 3 and minus 2. So let's say minus 5 halves. We would have 3 times minus 5 halves plus 6, all divided by 2 square roots of minus 5 halves plus 3. The top is negative, the bottom is positive. So this would be less than 0. And we have now determined the desired intervals of increase and decrease. Our function f will be increasing wherever f prime is positive, and decreasing wherever f prime is negative. And also note at this point, for the critical point at minus 2, we can classify it using the first derivative test. At minus 2, we can note our function is going from decreasing to increasing. And by the first derivative test, that guarantees we will have a local minimum when x is equal to minus 2. So for part B, we have a local minimum at x equals minus 2. And just to help us with our graph in a few minutes, let's note the function value at minus 2, going all the way back up to f, would be equal to minus 2 square root of minus 2 plus 3, which is simply minus 2 because 3 minus 2 is a positive 1. And this brings us to part C, where we want to determine the intervals of concavity. And as we already have the second derivative simplified down, it's a matter of determining where that second derivative is positive and where the second derivative is negative. So we start by setting it equal to 0. And note once again, a fraction is equal to 0 precisely when the numerator is 0. And in this case, that would require x to be equal to minus 4. But note, we're not interested in what happens at minus 4 because our function's not defined there. So all we need to do is consider the domain of our function. So to the right, this minus 4, which I'm going to write down momentarily, we can just cross off. This is not in the domain. And note, now if we pick one sample point, doesn't matter which one, or even by inspection in this case, and that should have been f prime above, f double prime of 0, say, would be equal to 3 times 0 plus 12, which is positive, over 4 times 0 plus 3 to the 3 halves. And f double prime of 0 is positive. And because 0 is a sample point in that interval from minus 3 to infinity, we know that f double prime will be positive everywhere in that interval because it's never equal to 0 in the interval. And that guarantees that we are concave up on the interval from minus 3 to infinity. And let's now put this all together to sketch a rough graph of our function. And note at this point the graphs do not have to be perfect, far from it, but hopefully they can get the general idea across. In our next few sections, we'll explore how we can do this even more accurately. And the first thing I'm going to do is kind of just indicate the information that we've gathered. We know from minus 3 to minus 2, our function is decreasing. And from minus 2 onward, it is increasing. And we also know that we are concave upward everywhere in the domain. And we have a local minimum at the point minus 2, minus 2. And just to give myself a couple other points to deal with, I'm going to evaluate f at 0 and minus 3. So just note f of x is equal to x square root x plus 3. So one could very easily get f of 0 is 0 and f of minus 3 is 0. And when it comes to sketching the graph of a function, as we will discuss, finding x and y intercepts is oftentimes quite helpful. So our function starts off at minus 3, 0. It's concave up and it decreases until it hits that local minimum. Then the function increases, passing through the origin, and remains concave upward. And this provides for us at least roughly a sketch of the function. I will note that these problems are fairly tedious in the sense that they require us to find multiple derivatives and analyze those derivatives. So it is definitely useful to practice these problems and to take your time with them. If you have questions, do not hesitate to reach out. Stay tuned and take care.